Good morning. In this section, I will be discussing about the two most commonly used chromatographic methods in research and analytical laboratories. The one is the gas chromatography. As we discussed during the classification based on the mobile phase and stationary phase, there are two types of the gas chromatography. One is the gas chromatography, one is the gas liquid chromatography, and the other one is the gas solid chromatography. The more important one at the application level is the gas liquid chromatography. Therefore, GLC is simply referred as the gas chromatography. In gas liquid chromatography, the mobile phase is a gas and the stationary phase is a liquid immobilized on a surface of an inert solid support. So, simply it is a liquid gas chromatography. The technique is based on the differential partitioning of the components of the sample in vapor phase between the mobile phase and stationary liquid phase. This causes a differential migration of the components, thereby affecting their separation. The liquid stationary phase is immobilized is generally a non-volatile, high boiling liquid like methyl silicon or polyethylene glycol. So, why we are using the gas chromatography or why the gas chromatography is so important? This technique has a strong separation power and even complex mixtures can be resolved into its individual constituents. The sensitivity of the gas chromatographic method is quite high. It gives a good precision and accuracy for the separation. The analysis can be completed in short time, within few minutes maybe, and the cost of the instrument is relatively low and the life is generally long compared to any other instrumental separation techniques. The technique is relatively suitable for the routine analysis of the many industrial and commercial samples. So, the component of the gas chromatograph. So, it is quite different from the simple chromatographic technique just like a plain chromatography or paper chromatography or thin layer chromatography. Here we are using a big instrument setup. It consists of a carrier gas. Helium is normally used as the carrier gas, or we can use the nitrogen and argon as well. So, in the instrument there will be a sample injection unit where we can introduce the sample into the injecting system. Then we can have a column there. Of course, it is a column chromatography, or we can say gas liquid chromatography, and we have another setup that is called the oven compartment where we can set the temperature program from the low temperature to high temperature profile. Then of course, we can have a detector to detect what it is eluting out of the column. So, the carrier gas is allowed to flow through the system, carrying the sample in the vapor state through the column. For selecting the carrier gas, there are following criteria, or there must be some consideration should be given to select the carrier gas. For selecting the carrier gas, the following consideration should be taken into account. It should be a chemically inert, that means it mustn't react with the component of the samples, or it mustn't react with the liquid stationary phase as well. It should be suitable for the detector employed and the type of the sample to be analyzed. It should be given the best column performance with the required speed of the analysis. It should be cheap and easily available and of the high purity for the separation. So, next is the sample injection unit. Here the sample is injected by the syringe through a silicon rubber diaphragm, or we can say silicon rubber septum in the injection pot. The injection pot is heated to a temperature which will ensure the rapid vaporization of the sample components, but it is noted that it will not degrade the sample components within this temperature range what we are going to use for the separation or the injection of the sample. The carrier gas is connected from the reservoir to a sample injection pot. Therefore, the sample vapors mixes instantaneously with the flowing carrier gas and is swept into the column. So, here in the column, the different components in the vaporized sample are separated from each other by virtue of their different interaction with the column packing. Just like any chromatographic technique, there will be interaction of the component between the stationary phase and the mobile phase. There are two types of the columns used in the GC or gas chromatography. One is the packed column and other is the capillary column. In the first case, or we can say the packed column, the supported column, the liquid stationary phase is supported on a small particles of an inert porous solid like material. So, usually the column dimension, or we can say the column, these type of the column is 1 to 10 meter long and have a 2 to 6 millimeter of the inner diameter. So, in the second case, that is what we call the capillary column. Liquid is coated on a capillary wall of the chemically modified glass or fused silica column. It is normally 15 to 100 meter in length and we can have a 0.1 to 0.53 centimeter inner diameter. So, next is the detector. So, after the elution or after passing through the column, we have another part, that is the detector. They are going to detect the whatever the individual components or the sample component coming by the carrier gas or the mobile phase what we use here. Here each component that come out of the column is immediately detected automatically by the high sensitive detectors. There are different type of the detectors that are used in the or that are employed for the gas chromatography. The most important one or most commonly used is the thermal conductivity detector, or we can say TCD detector, or it is called as a catharometer. The principle is based on the rate of the heat loss from a heated wire that is made up of platinum or tungsten that is placed in a carrier gas stream. So, when the carrier gas itself is flowing, it must have some thermal conductivity. So, once the sample components it is coming, it will change the thermal conductivity. It can be easily detected by these type of the detectors. It will give the signal for the chromatograph. We can identify the individual component according to their thermal conductivity. So, advantage of the thermal conductivity or TCD detector is that it responds to all type of the organic and inorganic components or compounds. It is a non-destructive detector. So, what we can have is after the TCD detector, whatever the effluent or whatever the carrier gas or mobile phase component or the sample component is coming out of the TCD detector, we can pass into another detector. Then we can identify simply by coupling these type of the detector with another identification techniques. So, the detector is simple and inexpensive, or it is the less sensitive, and biological samples cannot be analyzed by using these type of the TCD detectors. Another detector is the flame ionization detector, or simply we call FID. Ionization detectors are based on the electrical conductivity of the gases. So, FID is the most widely used and generally applicable detector for any type of the gas chromatography. It operates by the principle that there will be a change in the conductivity of the flame as the component is just burnt. With a burner that uses hydrogen air flame, the effluent or the carrier gas or the mobile phase that containing the samples from the column is mixed with the hydrogen and air, and then it is ignited electrically. The most organic compounds, when pyrolyzed or just ignited at the temperature of the hydrogen air flame, produce some of the ions and electrons that can be conduct electricity through the flame. So, the resulting current is then detected into a high impedance operational amplifier for the measurement of the signals. If you look at the overall process in GC, the sample mixture is injected into a injector pod where it is got vaporized and carried out by the carrier gas, or we can say the mobile phase, into the heated chromatographic column. During this process, the component of the mixtures get distributed between the two phases, that is the carrier gas, that is the mobile phase, and the liquid coated on a solid support, that is the stationary phase, depending upon the extent of the partition or adsorption. So, in this way the different components are carried at different rates throughout the column, hence they emerge out of the column at a different time or different rates. So, the time taken by each component to pass through the column is a characteristic property which help to identify the individual component, or we can say each component will take different time for their separation accordingly. So, they are detected by the detectors in which the recorder gives a peak for each component in the sample chromatogram. The size and location of the peak is an identification of the nature of the component in the sample mixture. So, the time taken between the sample injection and the analyte peak reaching a detector at the end of the column is given as the retention time, or simply we notify that by a TR. So, each analyte in a sample will have a different retention time or TR. So, the time taken for the mobile phase to pass through the column is called TM, or the retention for the mobile phase. A term called retention factor, K dash normally we call, or is often used to describe the migration rate of the different analyte component through the column. So, you can also call that factor is a capacity factor, and the retention factor or capacity factor for the analytes, for example, analyte A is given as K dash A is equal to TR minus TM divided by TM. So, TR is the retention factor for the particular component, retention time for the particular component, and the TM is the retention time for the mobile phase or the carrier gas what it is coming throughout the column. When an analyte retention factor is less than 1, what does it mean? It means the elution is so fast that accurate determination of the retention time is very difficult. So, high retention factors, that is the retention factor greater than 20, means that the elution takes very long time. Ideally, the retention factor for an analyte for the experimental setup will come between 1 and 5, that is varies within the time frame of the separation technique what we are using. So, we define a quantity that is called selectivity factor, that is we are simply called A, which describe the separation of the two species. For example, we have a two component A and B, so we can rate the separation efficiency accordingly. So, we are given an equation that is separation factor or selectivity factor A is equal to K dash B divided by K dash A. So, that is the retention for the component A and retention for the component B. So, it is the ratio of the retention factor or retention capacity factor of the two components in the given mixture. So, when calculating the selectivity factor, if the species A elute faster than species B, the selectivity factor is always greater than 1 we can see. Next is the application of the gas chromatography. Gas chromatography is widely used to test the purity of the organic compounds. Presence of the impurities can be evaluated by comparing the spectrum of the reference sample you have taken, that will be going to compare with the sample mixture what you have with you. Gas chromatography can be coupled with the spectroscopic technique like IR spectroscopy, NMR spectroscopy and even mass spectrometry as well, that will help to identify the exact nature of the chemical nature of the component what it is coming out from the column. Gas chromatography can be coupled with the mass spectrometry. It is widely used for the analysis of the hydrocarbon fuels, perfumes, flavors and fragrance chemicals. GC is widely used to study the extent of the air pollution. By using GC, the ethyl alcohol content in the blood can be determined with a high accuracy. GC can be used to identify the banned drugs that is used by the athletics. This can be easily and very fastly can be detected by using the GC analysis of the blood sample or urine sample that are taken from the athletes. Another most important chromatography technique that is used widely is the high performance liquid chromatography. HPLC is used for the separation of organic compounds which are non-volatile in nature. So, we are using the GC for the components that are volatile. If the sample component are not volatile, we can't use it for the GC separation. We have to use another method, that is the high performance liquid chromatography, or simply we call HPLC. Originally it was referred as the high pressure liquid chromatography, since high pressure is used for pumping the mobile phase throughout the column or the stationary phase. Due to its high efficiency and performance, high pressure liquid chromatography is referred to a high performance liquid chromatography. So, commonly it is known as HPLC, high performance liquid chromatography. So, as you can see, just like an instrumental setup I have given here, we can have a degasser. That means we have to, some of the dissolved gas we have to remove from the solvent phase, whatever the solvent phase we are going to use as a mobile phase. Then we have a pump that must be pumping the different type of the mobile phase what we are going to use. Then just like in gas chromatography, we have the injector system that will select the sample and will be injected into the column. Of course, there will be a HPLC column to perform the separation that must be kept inside an oven in order to keep at a constant temperature. The separation will be going to do in a constant temperature. So, as I told before, this is a separation based on the adsorption mechanism. So, here we have to use a gradient elution for the separation. So, in the case of the adsorption chromatography, we were saying sample component will be interacting or adsorbing on the stationary phase according to their interaction, according to the nature of the sample components. If some of the components are strongly adsorbed, will stay on the column, others will be simply eluting with the mobile phase what we are going to use. So, in order to take it out, or in order to separate, or in order to elute the sample component that is adsorbed on the column, we have to use another solvent or another mobile phase. That is why HPLC normally we says it is a gradient elution. In the case of the other chromatographic technique, we are using only a single solvent, that is called a isocratic elution. So, in the case of the gradient elution, you can choose a mixture of the different type of the solvents. Maybe you can use a 2 solvents, or we can use a combination of the 3 solvents, or maybe we can use a combination of the 4 solvent as well, in order to get the complete and efficient separation of the individual component that present in the sample mixture. So, principle of the HPLC separation is either adsorption or partition. A liquid or solid stationary phase can be used here. Most of the separations are based on the gradient elution, as I explained, or the mobile phase containing mixture of the solvents. Commonly used detectors are the refractive index detector, UV visible detector, conductivity detector, or electrochemical detectors as well. But main cases, what is the difficulty with associated with the HPLC separation is that here we are using a mixture of the solvents or mixture of the mobile phase. So, some time it will make some disturbance to the baseline of the chromatogram what we are obtaining by using the refractive index detector, UV detector or conductivity detector, etc. So, we have to employ a special detector that is called a evaporative light scattering detector, that will be just simply removing whatever the solvent it is coming out. Instead of that one, it will be detecting only the solute particles, or we can say simply the sample component by using this detector. This is quite a costly detector compared to any other detector, but there is no choice. If you are employing a gradient dilution for the chromatographic separation, we have to use the evaporative light scattering detector for the identification of the individual components eluting out of the column. So, as we can see here I have given the separation of the components. The color of the ball says the different chemical nature, and the size of the ball says the same molecular weight. So, here we have the separation. In the case of the size exclusion, we were having the separation not according to the chemical nature, according to the size of the sample. So, samples or here the dots or the balls having the same size, separated irrespective of the chemical nature of the samples. But in the case of the HPLC chromatography, here the separation mechanism is based on the adsorption. So, here the separation occurs according to its chemical nature. So, as you can see, firstly the red colored balls is separated, as you can get the nice separation or the individual red peak on the chromatogram. Then next is the blue colored dots, it is separated according to their chemical nature, and as I explained before, there is a slight dependence on the molar mass. Other than, we have a nice separation of the individual component in the HPLC chromatogram. So, as you can see in the chromatogram, we have a nice blue peak there. It is separated from the another component that is in green color. So, we got the separation, efficient and fast separation. As you can look at the time scale, maybe it is taking only few minutes to separate the individual component into its separated components. So, these are the most widely, because nowadays many of the analytical labs or research labs industry they are using, because as I told this, even though it is quite costly the instrumental setup, this is the very fast and efficient. Up to now, this is the only the known method that can very efficiently and fastly separate the individual component according to their chemical nature irrespective of its molar mass. So, the application of the HPLC mainly includes the qualitative and quantitative determination of the non-volatile organic components, and the purification of the chemical components, isolation of the natural products, and analyzing water pollutants and many of the any components that present in a complex mixture of the samples. So, if you compare this HPLC, as I told, this is a efficient separation and fast separation, and if you are comparing that with a molecular weight separation or molar mass separation, that is the size exclusion chromatography. So, in one separation we have the separation according to the molar mass, and in other case we have separation according to the chemistry. So, scientists were thinking to combine these two techniques. So, one direction we have according to the chemistry, other direction we have according to the molecular mass. So, they developed another type of the chromatography, that is the very most modern technique, that is called the two-dimensional liquid chromatography. In the first dimension, we have the separation according to the chemistry, or we can say we have the HPLC system in the first dimension. So, we are going to combine the HPLC system in the first dimension with another separation that is based according to the mechanical sorting of the molecule according to their size, or we can say the size exclusion chromatography or gel permeation chromatography. So, we are going to analyze the chemically separated components, and next step in the second direction we are using a GPC or we are using a size exclusion chromatography to determine the exact molecular weight of the individually separated component from a complex mixture. So, as you can see from here, we are going to separate according to the chemistry and we are going to separate according to the molar mass. So, you will be going to get a nice 2D plot in terms of the chemical nature of the component and the molar mass as well. So, this will give a quick, at a glance it will give a quick information about the what type of the chemical component present in the complex sample mixture and what molecular mass have the individual component. Two-dimensional chromatography is very important, even though it is quite expensive. At a single experiment or single chromatographic technique, you will get much more information about the complex mixture of a sample, what are the individual components present in the system as well. So, in this section we discussed about the most commonly used chromatographic technique that is based on the some advanced instrumental methods. So, first case we discussed about the gas chromatography, how we can use the volatile samples, how we can separate according to the gas chromatography. Then we discussed about the two types of the commonly used detectors, how we can easily detect the individual components, and based on the retention factor or the retention time, we can say we can have a particular retention time for the each components. Then we can analyze or we can identify that comparing with a reference material or reference sample what we can have. In the next case, we discussed about the high performance liquid chromatography or HPLC. That is very important because irrespective of the molar mass, we can just get a fast and efficient chemical composition separation of the component. This is the most important method. We can identify the component within very short time. So, we are using another type of the most advanced method, that is called two-dimensional chromatography. That is a most advanced instrumental method. Still it can give the most important information about the components that is present in terms of the chemical composition and the molar mass as well. I hope you enjoyed this section. Thank you for listening.